Hello friends, welcome back to VLSI Chaps. Previously, we discussed about memory management in operating system part 1, where we discussed how we can allocate a memory to the process in various ways. So that method we discussed was the contiguous memory allocation technique. We also saw various advantages and disadvantages of each and every techniques. What we can say is the common disadvantage that we found was the external fragmentation. Though we have a method of compaction by which we can reduce external fragmentation, but it is not an optimized or efficient solution for the CPU utilization. So now we will discuss about the non-contiguous memory allocation technique, in which we will be able to reduce this external fragmentation at a very high level. So let's talk about it. So one of the methods in non-contiguous memory allocation technique is paging. Now, why paging is required first of all? We saw that the common problem with contiguous memory allocation techniques are the external fragmentation. Now, though we have enough free memory available in the main memory, because of the process size is not equal to that available free space, we are not able to place that process within that main memory. That is the common problem that we are facing right now, which is the external fragmentation. Now, is there any way that we can divide the process in such a way that the fractions of the process can be fitted in with this main memory free blocks? If so, then the answer is yes. That process of dividing of one particular process into various fragments or parts, that is called paging. So we have a mechanism to store one process at different locations in the main memory to make system effective. You can see in the diagram that I have two memory blocks of 1 MB is available, which are free. Now if I have a process of size 2 MB waiting outside, though I have not contiguous blocks available, contiguous free blocks available, but I can divide this process into 1 MB of each parts and then can place these various fractions into these two different places. So this whole process is called paging. So now let's understand few terminologies with respect to these paging techniques. So we saw that we need to divide a process into various parts and fragments to have the optimized utilization of the CPU. Now, the parts which are supposed to be divided within the process are called as in pages. Now process is divided, so its equivalent main memory in which the process is supposed to be stored, that should also be divided. So the main memory fractions or the main memory partitions will be called as in frames. Now the only prerequisite here is the frame size and the page size, they must be equal to each other. The reason is, again, if the frame size is not equal to page size, then we might bump into the previous problems of fragmentation, which is internal fragmentation. So in order to fit one particular page into that particular frame, exactly that size, these both frame size and page size should be equal to each other. So this is the prerequisite. Again, previously what we were supposed to do is whenever any process is supposed to reside into this main memory, the whole process was being fetched from the storage into the main memory. Now because process is divided into various pages, rather the whole process, only the necessary or required pages will be fetched from the storage and then that will be placed into the main memory. So unnecessary operation of fetching and placing that won't occur here. On only primary or can say the prioritized parts of that particular process that is supposed to be placed in the main memory. If the main memory is available is having that free available frames, then that parts will be placed. So this is the basic difference between what we were doing in non-contiguous memory allocation techniques and this non-contiguous memory allocation techniques. To understand this process more clearly, let's see an example. So let's say I have a memory of 16 kilobytes and each memory is divided into 1 kilobytes of frames each. So here the frame size will be 1 kilobytes. And I have four processes, process A1, A2, A3 and A4. Each process is divided into equal parts which is also 1 kilobytes and this will be called as a page size. As we said earlier, the frame size of the memory and the page size of the process should be equal. So here they both are of 1 kilobytes. Now because we have 16 kilobytes of memory, each parts with 1 KB, we can have this process fit in. As on the diagram, you can say the process should be of 4 kilobytes of each. So you can say we are able to place four processes within a main memory at one point of time. Now let's say process 2, A2 and process A4, they both are in the wait state. They begin waiting state or can say the block state by which the CPU will be remain ideal. So this process is not working is not utilizing this CPU or the main memory. They can be placed outside and instead of that any other process that is whose priority is high and waiting outside can be placed with this process A2 and A4. So let's say that this is the new visualization of the memory block where I have taken out process A2 and A4. Instead there is one process A5 which was waiting outside and this process size was 8 kilobyte. So because A2 and A4 has left the memory, total 4 plus 4 is equal to 8 kilobytes of memory size is free. Now because we are using paging techniques, we can divide process in 1 KB of each and each 1 kilobytes of page can reside into 1 kilobyte of frame. So here we can divide process A5 into 4 kilobytes of each size and within these particular blocks we can fit each and individual page. So you can see now that process A5 can be able to fit in. Though we do not have contiguous block of free memory, this is distinguished from each other. They are apart. These blocks are apart. But still because with the help of paging, we are able to fit in the process, which of 8 kilobytes. So this is where the paging becomes more efficient and optimized, where we can utilize the memory in very efficient way to make the CPU operations faster. So this is what was the surface level mechanism of how paging works. One must have questioned that how internally this process is happening, how CPU or OS is able to know that I need to pick this page and I need to put that in at this particular address of the main memory. So to understand this, we need to understand few terminologies. Here there is an address space allocated to each page as well as each frame in the main memory. So the address space referred to the page will be called as a logical address and the address which is allocated to this particular frame that is called as a physical address. So main memory will only understand the language which is in terms of physical address. But CPU, which is supposed to access this particular page, will be knowing the language of logical address. So CPU first need to access this page or can say will need to access this logical address. And when it comes to placing that particular page into the main memory, it should be translated, this logical address should be translated into the physical address in which the main memory will be able to understand. So this address space translation is called address binding. So this is very important concept to understand the whole memory allocation technique. Here we are transferring one particular address space into the another, which is one logical to the another physical address. So how CPU will be able to do this? So basically logical address is nothing but just an address by which CPU will be able to know that okay, I need to access this page. So that is associated with that particular page. And physical address is the actual address where this particular page will be residing in the main memory. So to convert this logical address into the physical one, the main memory management unit comes into the picture. So every memory management unit will have its associated address translation unit, which will be able to translate this logical into the physical address. So let's say we have one particular MMU. We have logical address of that particular page is 346. This MMU will have one relocation register or the base register, which will hold some minimum physical address that is available. The reason is that MMU should not allocate or can say the translate a physical address which is not existing at all in the main memory. So it should be knowing the size or the limit of this main memory. So it will only translate the logical address into the physical address which is within that main memory limitation. So for that we will have one base register value. So in this case let's say it is 14,000. So this logical address of 346 will be added with this base register address, which will be the minimum physical address that is available right now. And we will get one another number. This number is nothing but the actual physical address where our process or the page will be reside in this main memory. So internally, this whole process is going to be executed within a microseconds. So based on the various OS, this memory or can say the relocation register base address might change. This is not fixed, but we can say this internal calculation will look something like this. So this is how the logical address will undergo a translation with the help of MMU or can say the address translation unit, and the output of this process will be the appropriate physical address or the location within this main memory. So in this whole process of memory allocation techniques, if you noticed one thing that we are constantly talking about one secondary storage whenever we are talking about the memory allocation. So you might wonder that what is this secondary storage? So there is another concept called virtual memory associated with that. Here, what is virtual memory first of all? It is nothing but one kind of memory management technique where this secondary storage like hard disk or solid state drive can be used as if it were a part of the main primary memory, which is RAM. So let's say I have one process. That process is definitely going to be reside in this main memory, but before that, that process will be stored in this secondary storage or can say as a part of virtual memory, so that main memory won't be required at that point of time because RAM is very limited. We have very less size of the RAM, so we are supposed to use it only when it's required at one point of time, not otherwise. So this virtual memory uses both hardware and software to operate. Hardware as in it requires one hardware space like I said hard disk or solid state drive. By software we can say there are paging mechanism which we understood previously. As a part of this paging mechanism, the software instructions or the software mechanisms will come into the picture where they are supposed to access this virtual memory. So let's say there is process going on in the main memory and one high priority process that is waiting outside and we need to prioritize that one first. So what we will do is we will remove the ongoing process. We will make that particular process that will be also in pages. So those pages of that process will be swapped from main memory to this virtual memory as in swap files. So virtual memory store those pages as in swap files of that particular process. So once this high priority process which we let in this main memory will finish its job, we will again switch back our original swap pages which are right now in the virtual memory into our main memory again. So there will be one swapping mechanism and switching, or can say, between the virtual memory and the main memory. So this swapping is quite slow when it comes to very frequent, or can say the large block of swapping these memory blocks. So because of that, computers with more RAM are considered to have better performance, because if their RAM size is higher, then we need to swap less particular blocks, because we will have the enough space to let another high priority process in. So you see that virtual memory is quite helpful in this case when it comes to prioritize the process and to store or temporary storage of that particular ongoing process. So I hope we understood the whole concept of memory management in detail. I hope you enjoyed this video. You can follow our platform on VLSI Chaps, and you can be the part of our community as well. Share the knowledge and let others grow their knowledge as well. So thank you for watching this video. Please do like, share and comment. Please do subscribe our channel as well. See you soon in the next video. Goodbye.